I would like to thank the directors, the last thank you from me for carving out a slot for marine biogeochemistry. Uh, it's very timely because to date, in my opinion, operational oceanography has benefited very little from marine biogeochemistry observations, and that's mainly because the observations made today to a large extent were driven by curiosity and the need to discovery rather than a strategized, thoughtful plan for monitoring. We knew very little about the processes and biogeochemistry phenomena, as well as the feedback loops that happen in the ocean up until really very recently. So no wonder that operational oceanography could not benefit from our observations. In this particular figure, you see first, as to the best of my knowledge, ever published an oxygen field based on a few observations made in 1927 by Meteor, a German vessel at the time, at 400 meters, I believe. And so this situation has changed rapidly over the past couple of decades. First of all, marine biogeochemistry knowledge, theoretical knowledge, has increased dramatically, but also tremendous improvement in our technology allowed us to measure these complicated variables, and therefore we now can actually start thinking of implementing biogeochemistry into the operational oceanography services. And what I will tell you about today is why we observe marine biogeochemistry, how we observe it, and also what exactly are the parameters that we decided are critical for our understanding of the ocean and also for societal benefit. As you can imagine, in 45 minutes, it would be very difficult to pack all the information that covers the whole marine biogeochemistry. So I mainly touch on subjects. I hint on them sometimes, and you at least will be able to look for an answer. You will know where to look for an answer. So I'll start by telling you that the marine biogeochemistry observations are part of what's the Global Ocean Observing System, basically, and this is any observation that's taken out there. And the first element of it is that it's built on requirements. So any observation is in a sense valid if it's made because someone requires information from this observation. It's obviously in situ and satellite, operational, and in biogeochemistry part of it, it starts to be operational, and research, which is the probably the biggest part of the pie for biogeochemistry, and linked to data management and most definitely product generation activities. In the GOOSE program, which is a coordination entity, we try to make sure that all the elements are advocated for at the highest level: United Nations conventions, Global Climate Observing System, several intergovernmental international bodies that we report to with the findings, with the needs, and obviously with proposals. We try to provide platform for collaboration, and me being here is one of such elements of this platform where historically physical oceanography-driven operational oceanography opens up to the new, in my opinion, opportunity, which is marine biogeochemistry. So this GOOSE strategy applies observations in three main themes. Climate, which is probably historically the biggest requirement for observations, but real-time services as well as ocean health, which is perhaps the newest addition to the requirements for observations. And as you can see in the vertical panels on this plot, biogeochemistry in the middle definitely contributes to the climate information generation, very little real-time services, and this will change with time, I believe, but today it is a very little contribution and very localized as well. And ocean health, it's relatively strong contribution from biogeochemistry. It's good to remember that any observation in one of the views of the observations could contribute to one of the three or all of them, the themes. And one more schematic which might help understand why we need to observe biogeochemistry and why we need to operationalize it with time. On this schematic, from bottom to top, you see one value chain of how one can see ocean research in general. So at the bottom, you have the blue sky research or curiosity-driven research, which goes hand in hand very often with technology innovation. And at the very top, you have societal benefit. So information mainly that policy and management and businesses need from all of us here in this room in order for the society to function better usually and sustainably. And in the middle, you have all sorts of elements of the chain, and as you can see indicated by a little logo, global ocean observations, sustained observations are right at the bottom of it, fundamental element of this value chain. Only from these observations you can start thinking about forecasts and early warning and services, as well as assessments, IPCC, scientific analysis, indicators of change, etc., etc. So GOOS is right here at the bottom, the observations part of it. I guess that Godae OceanView in general is higher up on this schematic on the left-hand side, and there's connection obviously in between. And GOOS also very strongly works with and advocates for the data assimilation and analysis, synthesis products and information product generation, as much as trying to help develop requirements for technology innovation. So we definitely in GOOS and in biogeochemistry think of societal benefit as our top requirement for observations. And in order to change the paradigm of observations that were mainly physical oceanography a few decades ago, in 2009, a group of colleagues attending what's called an OceanOps Online conference issued a call for change in this paradigm and developed a task team that wrote a framework for ocean observing. And this framework basically tried to rewrite how the observations are made, with the very strong focus on enhancing these observations by adding biogeochemistry and biological observations to the then existing physical observing system. And this document came out in 2012, so not so long ago. And a couple of sentences about what's in this document, as this is driving the development of biogeochemistry and marine biogeochemistry observations in particular. So the framework for ocean observing calls for a very simple systematic approach to observations. You need to understand what is your requirement, which is an input. Then you need to develop a process to deal with this requirement, which is in our case observations. And then you need to build an output, which is data and information product, which then informs the requirement and perhaps validates it or doesn't validate it, in which case the process needs to change. And this simple system can be obviously complicated a little, as in this slide. So the orange part now has three different elements: its requirements, phenomena, and essential ocean variables. I'll tell you a few things about it in a second. In the middle, you have a myriad of observing networks and observing elements, as we call them. These are this is the hardware in the water that measures stuff in a coordinated or perhaps not that coordinated way. And then in the green part, you have the data information products, but you have a couple of arrows there indicating that this whole process is only valid if the data and information product informs the issues that were asked in the first place. So this loop would go a few times around, and what we like to call it a system that's fit for purpose. So the purpose comes first, and then we try to fit the system to this purpose. So before OceanOps 09, before we understood that physical oceanography is not the only need of ours, the major driver for observations was climate and weather, and the various services related with weather systems were developed, and also various assessments and observation analysis efforts to do with climate variability, short-term, mid-term, long-term, you name it. However, obviously over time, once we started as a community, started to understand the ocean and climate more, we saw that there is much more to our requirements than just climate and weather. We have fisheries to worry about, and there's a lot of information that could be gained from observing certain parameters. There are regional priorities that are very specific to certain basins or regions. Real-time services, obviously, as in operational oceanography. And also perhaps long-term assessments and management of ecosystem services. This part requires very long-term observations, not necessarily related to climate at all, however, of similar quality. So all this meant that we cannot answer to these requirements by physical oceanography measurements only, and there was a call to marine biogeochemists to set up a panel, a goose biogeochemistry panel, to develop specific requirements for observations and develop the whole idea of what to measure and how to measure it. And so IOCCP, the program I coordinate at the moment, was asked to lead this effort, and over the 3-4 years following OceanOps 09, and specifically the publication of the framework for ocean observing, we did all sorts of community validation workshops, town halls at big ocean sciences meetings and webinars, and gazillions of emails and exchanges and individual exchanges with experts, etc., etc. We also were involved with development of what's called societal development goals, and this is a lingo of United Nations for today, which the goals for societal sustainable development, were developed in order for our not only scientific but also policy community to try and direct our living on this planet towards a more sustainable path. And one of those goals is life below water, and that's great news for us all. Hard work for some of us. We were lucky to be involved because we could steer some of the elements of the language. And as you might know, whatever gets into this language is then often taken more seriously by national governments. And as you know probably as well, most of what we do is funded by national governments, even if the agreements are international. And societal development goal, sustainable development goal, 14, has 7 parts to it. One of them is ocean acidification, which is high-level theme at the moment, but hidden in others is also oxygenation and nitrous oxide and all other cycles that are critical to understanding feedbacks between climate, ocean, weather, etc., etc. So this language within these documents, and obviously we don't have time to go into that, and also these consultations with the whole community for a couple of years made us come up as and agree upon as a community on those major 6 requirements for biogeochemistry measurements. And they're divided into 3 major or overarching or umbrella themes. The first one is to do with climate, and so this is the biogeochemistry part of the climate variability monitoring. The second one is very much focused on deliverance services, and I think as far as operational oceanography goes, this is where most action will happen over the next decade or so. So how large are the ocean's dead zones, oxygen minimum zones, and all other related deoxygenation issues? And how are they changing? How are they affecting ecosystems around them? What is the interaction between life and biogeochemistry, etc.? And the second one is what are the rates and impacts of ocean acidification? And obviously there is a lot of language behind this very general title. And again, this is to do with life, with ecosystem shifts, etc., etc. And for that, we'll definitely need to develop services that will allow local management to act quickly, promptly, in real time. And the third one, again, a bit different, which is the biomass of the ocean and eutrophication and pollution, which is very close to our shores usually, but very difficult to predict and act upon in real-time mode. So this is exactly why we do biogeochemistry observations in a long-term monitoring mode. Now, you have to observe a phenomenon to be able to answer any of these questions, and there is a series of phenomena you need to observe. So we've came up with a definition of a phenomenon, which I don't think you have to memorize, but we basically want to observe a process or an event or even a property that has some characteristics, spatial and time scale, but can be measured by what's called essential ocean variable, and I'll move to those in a second. But what's critical here is that this event or property needs to answer at least one of the scientific questions asked on the previous slide in this case. And there's phenomena like deoxygenation, that's a process, or storage of certain matter, that's a property, or an event like a harmful algal bloom, which is something that needs very quick reaction very often. So there's also some comments about how it should be named, etc., etc. What we came up with is the set of phenomena that are in our interest. So this is what we will be focusing on, what we are focusing on in terms of biogeochemistry observations globally. And this is a global long-term observing system, and obviously this might vary a little if you think about your very local basin or sub-basin, because sometimes this is much more important than the global ocean acidification or deoxygenation or upwelling problem. There's strong connections with physics and climate and also with biology and ecosystem in terms of phenomena. So there are phenomena that will be measured for many purposes, and that's one of the main reasons why the framework for ocean observing calls for coordination and integration across disciplines, because we cannot afford to measure separately for various purposes, but we have to homogenize the understanding of why we measure it and what it is that we want to measure. And we try to work towards even stronger coordination and homogenization of this phenomena across disciplines. So now I told you a little bit more about what we want to measure. We know the phenomena, but to go even deeper, you don't measure a phenomenon, you measure a particular variable. And for each of these phenomena, as much as for each of the questions asked, you could measure really quite a few variables. And just to give you an example, for one of the questions that's to do with carbon content change, and you can measure 8, 10 variables, and some of them are obvious, like carbonate system, but some of them are less obvious, like stable isotopes. The same is true for the greenhouse gases, or perhaps for biogeochemistry and human impacts on biogeochemistry. In ocean acidification, for example, you might want to measure stable isotopes of protactinium, and this is something very obscure. A couple of labs globally can do that. That's for one. And one measurement costs around $100,000. So it's very not efficient to ask a global ocean observing system to measure all of these parameters. So we sat with all these people for these few years and thought how we could go around it. And obviously the answer was that there must be some proxy information in some of these variables that could be utilized. And so we can decrease the number of variables that we need to measure. And so we did. It's just some other examples of parameters that would need to be measured to very precisely describe answers to those questions. But as I said, there is perhaps a way to avoid having to measure 30, 40 variables on every single platform and having 30, 40 data streams going around. We looked at all these variables via this impact versus feasibility scheme, where high impact means that a measurement would give us enough information to describe one of the phenomena. And then feasibility, again, is what can be done. As I said, there are some measurements that could be done by a couple of labs globally, and there's some that could almost every lab out there could do. And one has to take this into account when one is trying to design a global ocean observing system for biogeochemistry or any other. And that's what we did. We weren't the first one to do that, actually. We came up with what's called essential ocean variables in blue here on this slide. But long before, there were essential variables that World Meteorological Organization used in green on this slide, and essential climate variables, some of which are also essential ocean variable. And there is now actually a strong move. So we actually are victims of the success of this essential variables idea, because Southern Ocean team has developed their own essential variables, an Arctic essential ocean variable, Atlantic essential variables, etc., etc. So we try to stop the train, because the word essential loses its potential, and that's not good. We want to make sure that we call essential what's really critical to observe, and everything else could be regional measurement that's needed for some answers. That's mainly because if we manage to stick to this essential that's relatively small, we will be able to leverage resources to actually implement the observing system for these variables. And again, we've developed a definition that's basically saying that a good essential ocean variable is totally necessary to assess state or change in one of the phenomena. That's it. Without it, you cannot do any phenomena, the individual phenomena. So it's not to better assess, it's just to assess a phenomenon. Well, finally, this is what biogeochemistry observations are going to be focused on for the next quite a few years, I would say. These are 9 essential ocean variables that came out after years of consultations and discussions and development. And I will spend the rest of this talk, of this lecture, trying to tell you how we measure those and how we think we might measure them in the future. And I will hint a little bit on the data streams that are being developed. So it's work in progress, most of it. Each of these essential ocean variables has a different state of readiness, and by readiness I mean some of them we can measure everywhere. Some of them the technology is in a prototype. Some of them we know how we want to measure them, but there's not even a prototype. So the prototype or the concept to mature is what we as coordinators try to focus on. We try to make sure that whatever idea is in a concept stage is being moved to mature stage, and it's work in progress. As I said, as you see, there's quite a few variables to worry about. There's vertical and horizontal resolutions, temporal resolutions, etc., and different questions require different answers in terms of this resolution. So there's quite a lot of work to do. However, we think that by knowing exactly what we want to measure, we are way into the game, and we will figure out with time how to do that. This readiness level is something that's common in technology, as you probably know. Technology development, the framework for ocean observing describes the readiness level not only for the actual observation elements, so platforms and sensors, but also for the requirement setting. So is the requirement for certain measurement justified? Is it validated throughout the community, etc., etc.? It's important to know, because some of the requirements are very localized, for example, and we should not forget that what we are talking about here is the global ocean observing system. And similar readiness level assessment goes on in the data management and data and information product developments, which is critical, obviously, in order for the whole system to make sense. But I would say it's the least developed at the moment, maybe because the amount of data that's coming out of biogeochemistry observations every year now is bigger than every decade 10 years ago. So we have to learn how to deal with this amount of data. And in physical oceanography, big data has always, or maybe not always, but has been around for a while, whereas this is something relatively new for biogeochemistry. Okay, very quickly, each of these essential ocean variables, if you ever need to know more about it, has what's called a specification sheet. This is just an example for oxygen, and it gives you information about things like what could be derived from this particular observation. What are the supporting variables, for example, that you need to measure in order for this particular measurement to make sense and give you most information. It also goes into the requirement setting. So what are the societal drivers for measuring this variable? What are the scientific applications? And what's the readiness level of this requirement, as I hinted on just a second ago? Then what are the phenomena to be captured? And obviously each phenomenon would have a different scale in temporal and spatial, and therefore an oxygen measurement done to quantify earthy flux would be of different resolution, temporal and spatial, than the one made for assessment of changes in the storage of O2, etc., etc. So all this information has been developed by experts. It's available from GOOS and IOCCP websites. I won't go into too much detail about it here, at least not now. But I guess it's worthwhile for anyone who would want to, for example, start using oxygen for certain development of services, to look at them and figure out what could be done and how it could be done. We also name the observing elements. So what are the observing networks, like profiling flows, repeat hydrography, moorings, gliders. These networks measure oxygen, and some of them are mature, some of them are pilot. They have different resolutions, temporal and spatial again. They also measure different sets of additional or supporting variables, which is important when you create a data product. And there is some information about the sensor technique or methodology. There's some information about the future observing elements for any particular essential ocean variable, as well as you can see, relatively empty data and information creation matrix. And when you look at gliders, for example, we know that we can measure gliders, oxygen from gliders, sorry, and we do measure oxygen from gliders, but we are still in a very early development stage of the whole oversight and coordination, data quality control schemes, data management, etc., etc. So this is still to be developed. We work together amongst all these observing networks to make sure that one day we will be able to look at all this data from one place in your office. But that's utopia of the future, for now at least. So this is a small hint on how you can have a look at the biogeochemical parameters being measured out there. Now a few words about the observing networks that we utilize. Then probably one of the two most traditional networks for us is the underway initially CO2 observations. So these are ships of opportunity, commercial vessels taking bananas from one place and cars from the other place. And we install instruments on those. And historically CO2, now oxygen as well, nutrients as well. And this is obviously our surface measurement. So we cover the surface of the ocean with these measurements, and increasingly with increasing number of parameters as well. However, as you can easily see even from this plot, the coverage is not that great, and we cannot really change it that much because trade goes on where it goes on, and one cannot just change the ways that trade works, and so we are limited here. Surface ocean interior, different story. These lines here are all research vessels, so 10 times more expensive observing network. However, we can go exactly where we need to go. The parameter suite is much larger as well, and with scientists on board, the accuracy of the measurements greater again. And so this network gives us information about biogeochemistry observations in the ocean interior. Again, historically, ship-based observing networks. So we would now have surface and ocean interior covered. And both of these networks, neither of these networks actually measure all of the 9 essential ocean variables yet. We are slowly moving towards that, I hope, at least regionally for now. It's mainly because of technology development, but also because it's costly, more costly, and the requirements needs to be critical for any government to spend more money on observations. They need to see the benefit of this observation being made, and hence the whole idea of starting with the requirement setting rather than starting with curiosity or the need to discover. Now, moving to autonomous platforms. This is just to show you that there's moorings that measure biogeochemistry out there. And again, mostly historically carbon, then oxygen, and then nutrients, and now increasingly other parameters in the carbonate system and outside of the carbonate system. As you can see, coverage in critical places of biogeochemical processes in the ocean, but much less coverage outside. And so, again, interpolation, extrapolation required hugely in order to draw maps of global change in processes and phenomena. So these are moorings, and last but definitely not least, the new kid on the block, which is called Biogeochemical Argo. I'll spend a couple of minutes more on this particular network, as it seems that in terms of coverage and number of parameters, this is going to be the game for biogeochemistry in the near and further future. This is a plot from January this year. The numbers haven't changed that much. So it's about 300 floats that have up to six biogeochemical parameters measured on them. If you compare it to 4,000 Argo floats, it's a tiny fraction. However, the group here thinks that 1,000 of those would suffice for us to actually address the questions we asked. It's very, very, very long process to move from one parameter to two parameters to three parameters, etc. Battery life, sensors, their accuracy, calibration, validation of the sensors, drift, bias, etc., etc. This network, as I said, in opinions of many, will be the game of the future for biogeochemistry, but it will never be able to exist without the repeat hydrography sections that I showed a couple of slides back, where very high precision measurements are taken and used to calibrate, validate those float-based measurements. So as I said, from Argo to BioArgo, it's a long way. It started in 2008, so not that long ago, by this IOCCP, which is the Ocean Color Coordination Group, and they came up with a working group and a report that they want to add biooptical sensors on Argo floats. They justified it and described how it could be done. Then there was another big workshop in the States, run by the US Ocean Carbon Biogeochemistry Program, where further development and description were made. And in the implementation plan, the research topics for biogeochemical Argo are very, very similar to what the whole of biogeochemistry observing system is focused on. So carbon, oxygen and nitrate, acidification, biological carbon pump, and then shift of community shifts, and so impact on the ecosystem, simply speaking. And to address management, carbon budget verification, and living marine resources, this is food and ocean climate feedback. So what we measure on these Argo floats, biogeochemical Argo floats, you see here, and again, if you might remember from the EOVs, we have oxygen, nitrous oxide, pH, which is part of the inorganic carbon system, chlorophyll, suspended particulates, and downwelling irradiance. So these are the parameters that I believe will be the most available data source for the next 5-10 years before we start being able technologically to add to this six. It's not the complete list of essential ocean variables, but that's good enough. And just to remind you, it's about 1,000 floats that, according to experts and those involved in the BioArgo program, that we need globally. And in order to sustain 1,000 floats array, we would probably need about 250 floats a year in the water, because, as you know, the float dies after some time. You don't recover it. You usually don't. Some people were lucky and did recover a few floats, but that's not in the budget when you start it. And one float fully equipped is about $80,000, so it's relatively costly endeavor. However, if you think about 1 day on a research vessel, it's one float per 1 day, more or less. So depending on which perspective you take. And this is how it looks like. I guess you might be familiar with Argo floats, or maybe even with those floats. It's packed. It's basically packed with sensors. Huge energy demand. A lot of places where things can go wrong. A lot of need for validation, etc. So, data management for biogeochemical Argo is a huge task. And as we speak, there are guidelines developed and manuals and community-driven efforts to actually assess the quality, improve the quality, etc. Because once you stick this thing in the water, it stays there for a couple of years, 3 years at times, perhaps even longer, we'll see. And you have no way of calibrating and validating. So when you actually do stick it in the water, you need to be pretty damn sure that it gives you the right number and some error estimate as well. And it's very difficult. I don't know why this black thing comes up. I just want to tell you, I think I'm running out of time soon. I have a few more slides. I hope it's okay with you guys. Ananda, whenever you think I'm done, just tell me and I'll quickly move to the finish. So just one example. Oxygen, you can measure it by not only several methods, but within a method, there's several manufacturers, obviously, and they use different technology in it. And it's relatively uncoordinated. Everyone goes after the top spot. We try to make sure that certain standards are kept, but only by using certain products enough time, we then establish what does work, what doesn't work, and it is the most labor intensive manual method that's called Winkler titration gives the best result, but only if the person knows what they're doing. And the same result might be obtained with an optote that you just stick at the end of your float and throw into the water. And so there's various elements that error can be added to the whole measurement. And whenever you deal with biogeochemistry data from sensors, please remember to ask as many questions as possible. What was the calibration? What was the validation? How was the data obtained? Because very often, unfortunately, so far, these are numbers, but these are not observations, because they don't have any error estimate on them, and you have no clue whether what you see is a real thing or not. And there's ranges of parameter, there's accuracy requirements, long-term drift accuracy. You need to know for the duration of deployment, few years, what's the drift going to be? Is it acceptable or is it not for whatever you actually use your data for? And the response time, is it important for you that what you see is from 200 meters below, or is it not, or 50 meters below? And again, the reference to calibration is critical, and we are still developing various methods of calibrating not only oxygen sensors but any other sensor. Okay, so this is how we measure it, and finally the data. Again, data historically carbon. So 10 years ago, the biggest to date marine biogeochemistry data endeavor started, which is called SOCAT, Surface Ocean CO2 Atlas. We just celebrated 10 years anniversary in Switzerland during the ICDC conference in August. It's the 5 of the data set. It's rather independent of any other data sets or data streams, which is perhaps to be changed, hopefully. It has so many million data points. Every single data point is quality controlled, which is a sweet thing if you want to use the data for product development. It can be downloaded in all sorts of formats, and it's very well documented in papers and reports. We've automated the whole process, so it's relatively easy to download as much as upload the data if you're doing the measurements. You can go online to SOCAT, you can play online with the live access server thing. You can download it to your system with flags, with comments, and work like that. We try to make sure that people can use the data we produce to develop their products and to attend to their needs. And so it did start to happen. As I said, we started SOCAT in 2007, and with time, more and more applications, including Ocean Carbon budget, which is released every couple of years, is now using SOCAT, and we were asked to make a voluntary commitment to the UN Ocean Conference that we will produce SOCAT every year for the foreseeable future. So it seems like it's working. As I said, it's only carbon at the moment, and we would like to expand it to all the other essential ocean variables, but that's again time, and I don't think you'll see any of that happening within the next couple of years. I think maybe half a decade. That's what it will take to see oxygen or nitrous oxide in this form and quality controlled and available. And that was the surface of the ocean. Now the ocean interior, what we call GLODAP, the data set, has all the data from the repeat hydrography cruises I showed you on one of the slides. It has more than just carbon. It has nitrate as well, and silicates, some nutrients, inorganic nutrients. It has oxygen. And again, quality controlled by the community, documented in ESSD papers, so you can go out there, you can see exactly what happened to the data, what are the changes that were made to the data, what's the internal consistency, etc., etc. So there's this product for ocean interior, and you can start producing data-based fields that you can then compare with your model fields, for example. The whole carbon data management starts to look like something that has a plan. This slide is just to indicate how many players are there around the marine biogeochemistry data production and management. And what we try to achieve is indicated here on this schematic, where various observing networks having underway or discrete samples get onto one stream to what's called the GDAC for ocean biogeochemistry. Data is in all separate places, but you can access it actually from one particular portal. That's who's doing it. I think there is a problem with my Microsoft. I have a couple of more slides, if that's okay with you. I don't know whether you can still see me. I will try to open my PowerPoint again and finish the presentation. Just give me a sec. I don't know why it closed, but it did. Okay, I'm trying to open it. Okay, it's open. Okay, Ananda, can you hear me? Yes, I can. My PowerPoint just closed. Ananda? Okay, I just have a couple of more. I just have a couple of more slides, if that's okay with you. Yes. Yeah, okay. So I hope you see this slide, which shows you for Argo, because I guess it's important, especially for operational oceanography, that for Argo, each of the parameters there is data management documentation developed, which is basically published with a DOI. And as you can see in green, these are the data management documents that are already finalized. The yellow one are ongoing, and the red ones are still to be done. And so for each of the parameters, there will be real-time and delayed mode and DAC level, data assembly center level data management documents developed, so we know exactly what's out there, because this we think is critical in order for us to be able to produce numbers with error estimates. And just the final word is that in the future we think that it will all go towards our efforts will go towards two things. One is what's on this slide, which is not this particular hardware, but basically a sensor suite. All the sensors packed in one sensor, basically. This is what seems to be happening now, that developers seem to start packing those sensors into one pack, and it will be much easier and much less battery consuming for the future. And the second item that is definitely in front of us is the observing system design element, and I will not talk about it, not only because I don't have time, but also because Johannes Carstensen will come to Mallorca on a Sunday and we'll talk about it early next week. And with that now, thank you very much. Sorry to run over my time, and if you have any questions, I'm open to hear them.
So thank you, Maciej. Is there any question? Well, yeah, I think we have one. So she's coming to the computer. Be careful.
Yeah. Hi. Just actually questioning in regards to the parameters, with regards how you choose them. And because the need of today might not be the need of tomorrow, and some people will come with, okay, discovery, and then, oh my gosh, and then, oh, we wished that we had that for a long time before. And then, for instance, I've just noticed, like you, or you plan, or you have already like a backscatter on BioArgo. So what type of, like, why do you choose such or such wavelength? You know, because there's so much application, and then some people would want to use such wavelength, others would need others. So yeah, here you go.
Yeah, it's thank you very much. Great question, and we are after a moving target. So what you're describing is that what we think we need to measure today won't be what we need to measure tomorrow, and I agree with that completely. And the idea here is that every couple of years we reassess the fitness for purpose of the system. So today we know what are the requirements, and we have listed them in this very high level hierarchical mode. So we know why we need to measure today, and we build the system towards that. But at the same time, there is development going on locally for things that are definitely not in the essential ocean variables mode today, but people think that there will be. And once the requirement comes that, well, we actually don't need to worry about deoxygenation, but we really need to worry about plastics, we will definitely change the paradigm to move from deoxygenation to the pollution more. This is not set in stone system. It's flexible, and it's driven by the requirements and also by technology development. So it will be a moving target. Every couple of years, we hope to reassess the system and see whether we're doing well or not.
Thank you.
Thank you.
Thank you. Any other question? Yeah, another one.
Hi.
So,
How do you see the assimilation of this great biogeochemical data set into models? So either into forecast models or into reanalysis?
how do I see it technically, or why would one do that?
Sorry?
So your question was about how do I see the assimilation efforts technically, or why would one want to do that?
Yeah, of course, technically, yeah.
Right. So technically, I'm afraid I would not be able to answer your question because I don't do assimilation myself. I can only hint that there's already needs to assimilate this data for the coastal management systems, where you have, for example, aquaculture that needs to know in a very quick feedback loop, like days more than weeks, when certain upwelling regions are coming or upwelled waters are coming to the coast because they need to change the water in their aquaculture, baths, etc., etc. So if you did not ask this question, why, this is the answer, but how it's done, I'm sorry, I cannot answer.
Okay, thanks.